Hello there, Mr. Sutton here, bringing you the AB Calculus 510 homework solutions on FTC integral evaluation with polynomials. For this weird problem, we're given the integral from 1 to 2 of some function of x minus c being 5, and we're also told this other function, just f of x without the minus c in there, with these other limits of integration is, well, that's what we're trying to figure out. So we know the most about this integral expression. Let's actually use our fundamental theorem and expand this a little bit and see what it looks like. So the antiderivative for f of x minus c is going to be big F of x minus c. The function inside here, it's not just x, but the derivative of this thing is just 1. So we don't really have to worry about this inner function, we just leave it in there. And we still have the same limits of integration from 1 to 2. Plugging both of those in, I've got big F of 2 minus c minus big F of 1 minus c. And there isn't really any further I can go with that other than to say that this expression equals 5. Okay, how about this other expression? So the antiderivative of just f of x is even easier. It's just big F of x. Same limits of integration from 1 minus c to 2 minus c. Plugging both of those in, I've got big F of 2 minus c minus big F of 1 minus c. And if we just take a step back, we realize these are actually the exact same thing, which means they should have the same exact numerical value, which is 5. So choice B. For this problem, I'm given that the integral from a to b of f of x is a plus 2b, and I want to use that information to figure out the integral from a to b of f of x plus 5. Now, unfortunately, there's no quick way to do this problem. If you look at answer choice A, they're just like adding 5 there. No, it's not that easy. To do this, we actually have to use our fundamental theorem and expand both of these expressions and then rearrange things. It's essentially kind of like a system of equations. So let's start with this first one here. Antiderivative of f is big F, and we're doing that from a to b. So we can write big F of b minus big F of a. And we were told that this was equivalent to a plus 2b up there. So I'm just going to write equals a plus 2b because that'll be important later. Now for this next one, let's evaluate it. So antiderivative of little f is big F. 5 becomes 5x. And again, we're integrating that from a to b. So plugging those in, I can write big F of b plus 5b minus big F of a plus 5a. So this is a slightly different expression. The key here is that if you look at all the answer choices, they all have just A's and B's in them. They don't have these big F's in them. So we need to find a way to replace this big F of B and this big F of A with something else. The clue is up here. When we initially did, we said that big F of B minus big F of A was equal to A plus 2B. So I'm just going to rearrange this stuff so that I have big F of B minus this big F of A. And then I'm not going to forget about the other stuff. I still have a 5b. I still have a minus 5a. But I have simply just rearranged things. So now I again see that this equals this. So I'm going to replace big F of b minus big F of a with just simply a plus 2b. And now I can combine like terms to get one of the answers. So this will be 7b minus 4a, which gives me, let's see, answer choice C.
For number 3, if f is a continuous function and big F prime of x is f of x, for all real numbers, then what is the integral from 1 to 3 of f of 2x dx? So this is pretty much straight up integral evaluation theorem FTC stuff with a little bit of a mini substitution thrown in here. So integral, or antiderivative rather, of f of 2x, that would be big F of 2x. But now since we have a linear inner function, we have to divide by the derivative of that. So this would be 1/2 big F of 2x, evaluated from 1 to 3. Plugging in 1 and 3, we've got half of big F of 2 times 3 minus half of big F of 2 times 1, or half of F of 6 minus half of F of 2. Now let's come up for air here and see if there are any answer choices that match what we've got so far. So looking through my list here, I see choice E matches exactly what I have, so that's what I'm going to go with. For number 4, we're being asked to find the integral from 1 to e of this rational expression. To make my anti-differentiating a lot easier, I'm going to go ahead and divide each of these terms by x. So I can rewrite this as x minus x to the negative 1. And now I'm going to go ahead and use my reverse power rule on this, and then I can use my FTC to plug in e and 1 to whatever I get. So I've got half of x squared, and then minus, this is going to be ln of absolute value of x. So now I'm plugging e into both of these, and then subtracting what I get when I plug 1 into both of those. And if I look at what I've got here versus the answer choices, on the free response, what I've written here would be perfectly fine, but clearly we need to simplify this a little bit to match one of the answer choices. So going through, half of e squared, can't really do much there, but ln of e, we know that's 1. And then over here we've got minus, this is just 1/2, and ln of 1 we know is 0. Still doesn't match any answer choices, but we're getting warmer here. So e squared over 2, and then these numbers here, these can be combined, right? Negative 1 minus 1/2, that's just negative 3/2, and that's going to match answer choice E.
For this problem, we're trying to take the integral from 1 to 2 of x squared minus 1 over x plus 1. So this one looks kind of tricky at first glance, but if you think back to what you had to do when you were taking antiderivatives, well, if we can simplify, it's often a good idea to do so. For example, this x squared minus 1 can be factored into x plus 1, x minus 1, which is important because these x plus 1s can cancel out, leaving us with just the integral from 1 to 2 of x minus 1. The key here is that we have to stipulate that x does not equal negative 1. So we're going to try not to plug in negative 1 because there is a hole at x equals negative 1. The good news is that won't affect us on this problem because the limits of integration are from 1 to 2. So this negative 1 hole is not even in the picture. And just a little tidbit, even if it were, you can actually integrate over holes without affecting anything. Kind of neat. But moving on, let's integrate just this. So we've got, this will be, let's see, x squared, and dividing by 2, I've got 1/2 x squared minus 1x, and that's from 1 to 2. So plug in 2 into everything. Here's what we have for that, minus what we get when we plug 1 in for all this stuff. Now it's multiple choice, so we have to simplify this. Over here, this is going to be 4 times 1/2, which is 2, minus the other 2 just gives us 0. For this next bracket of stuff, this is going to be 1/2 minus 1, which is negative 1/2, but we're subtracting negative 1/2. So that means we're actually adding half to give us positive 1/2. And that'll give us answer choice A.
For number 6, we want to know all values of k for which the integral from negative 3 to k of x squared equals 0. So easiest way to do this one is to set up an equation by expanding this with the FTC, the integral evaluation theorem. So I need my antiderivative first to do this. Bumping up my exponent to a 3 and dividing by 3, that's going to be 1/3 x to the third. Again, evaluating that from negative 3 to k. And this is, again, an equation, so this equals 0. These two things are equivalent. Now let's plug in k and negative 3. So I'm going to have 1/3 k cubed minus 1/3 times negative 3 cubed. And simplifying this a little bit here, I've got negative 1/3 times negative 27, which is positive 9. Next, solving for k, I can subtract the 9 and multiply by 3 on both sides, so that's k cubed equals negative 27. And then cube rooting both sides, we get k equals negative 3. And that's it. So that's going to be answer choice A.
For 7, we're taking the integral from 2 to x of all this stuff. Now be careful. We have this answer choice right here, 3x squared minus 1, which a lot of people are going to pick because you're used to seeing variables in the upper limit and just kind of plugging that in for the letter of integration here. But we're not taking the derivative of this. This is just a straight up integration problem. So first we need the antiderivative of 3t squared minus 1. That's going to be, let's see, this bumps up to a 3. Dividing, we have just 1t squared, or 1t cubed rather. and then minus 1 becomes minus t, and that's from 2 to x. So all we have to do here is just plug x and 2 in here and subtract. So all this stuff with x plugged in, that's going to be x cubed minus x. And then we're subtracting all this stuff with 2 plugged in. And we just have to simplify the answer. So this stuff here, we've got 8 minus 2, which is 6. So at the end of the day, x cubed minus x minus 6 ends up being our answer, which is choice A. Here we go with this problem. Now, looking at some of the answer choices, you might initially be surprised to learn that this is a no calculator problem. But think about it, if they let you use the calculator, you really could just use the integral function on the calculator to do this. So they're going to make you do it out and throw some arithmetic your way. Let's take our antiderivative first. So this bumps up to x to the 4th. Dividing by 4, we've got 2x to the 4th. And for this next one, this becomes x to the 3rd. Dividing by 3, we have 1x to the 3rd, and that's being subtracted. Integrating that from negative 1 to 2, we have all of this stuff with 1 plugged in, minus all of this stuff with negative 2 plugged in. And now some arithmetic. This is just 2 minus 1, which is 1, so that could be a lot worse. Over here, well, negative 2 to the 4th is 16 times 2 is 32. So we've got 32 minus negative 8, so plus 8. So at the end of the day, we're just doing 1 minus 40 when all is said and done, which gives us negative 39, choice C.
For number 9, we're told that f is a linear function such that 0 is less than a is less than b, and we want to figure out the integral from a to b of f double prime of x dx. So using our antiderivatives and integral evaluation theorem, we can write this as f prime from a to b, and then that's just going to be f prime of b minus f prime of a. But what does this actually mean? Because this is not one of the answer choices. So here's where we have to look back in the problem, and they told us that f is a linear function. If f is linear, that means when I take its derivative, I'm just going to get some constant that was its slope, such as k, whatever the slope is, right? You could call it m if you wanted to. The point is that since we're taking the derivative of the same line twice and then just trying to plug different numbers into them, we're getting the same constant both times. So this is really just essentially k minus k, which we know to be 0. Choice A. For number 10, we want to know all values of x for which the integral from x to 2 of t cubed is equal to 0. So for this one, fastest way to do it is just to use our integral evaluation theorem and antiderivatives and set all that equal to 0. So antiderivative here, this exponent bumps up to 4. Dividing by that, we've got t to the 4th over 4, evaluating from x to 2, and that all equals 0. So expanding this, we've got 2 to the 4th over 4 minus x to the 4th over 4 equals 0. And now doing a little solving, I can multiply everything by 4, and then let's see, 2 to the 4th is 16. I'm going to add x to the 4th over to the other side. Just a whole bunch of algebraic steps at once there. Now I have to take the 4th root of both sides of the equation. So that's going to come out to, let's see, don't forget the plus or minus here. We've got plus or minus 2 when the dust settles. So that's going to be answer choice D.
For this problem, f is some function whose table of values is given above here, at least some of the values. We want to evaluate the integral from 2 to 13 of this stuff here, 3 minus 5 f prime of x dx. So we're just going to use our integral evaluation theorem on this one, the FTC. Let's take our antiderivative first. So we've got this 3 becomes a 3x minus, this will just be 5f of x. All of that integrated from 2 to 13. And now we've got all this stuff with 13 plugged in minus all this stuff with 2 plugged in. Let's evaluate each of these now. This will be 39, and let's see, what's f of 13? Well, it's 6. So 5 times 6 is 30, so we've got 39 minus 30 in that first group of numbers. Over here we've got a 6, and let's see, f of 2 is 1, so this is going to be 6 minus 5 times 1, or 6 minus 5, all that being subtracted. So this is just 9 minus 1, which comes out to 8. This problem looks a whole lot nastier than it actually is. So we're taking a closed interval from a to b, breaking it into n equal subintervals, and they've got all this verbiage here, and then we've got this limit as n approaches infinity, infinite sum of, we've got square root of x times delta x. So the key on this is realizing that they're just giving you the Riemann sum definition of a definite integral. This is just asking for the integral from a to b of the square root of x dx. This little delta x is essentially the dx, square root playing itself in this motion picture. And if you're taking an infinite number of rectangles and adding them up, you're just essentially taking a definite integral. So we just have to evaluate this using our fundamental theorem. So we need the antiderivative of square root of x. Well, radical x is just x to the 1/2. That bumps up to a 3/2, and we multiply by the reciprocal of 2/3. So we've got 2/3 x to the 3/2 from a to b. And now plugging a and b in, I'm actually going to take this 2/3 and sort of bring it outside. You're allowed to do that with constants out in front. You could have left it inside as well. It doesn't really matter. It's being distributed over subtraction. So we have then just x or b to the 3/2 minus a to the 3/2. And that's actually exactly what answer choice A is saying. So there we go.